Hello, my name is Markus. I'm from the University of Stuttgart, and I will present a paper, Optimal Medium Voltage Grid Planning under consideration of dynamic current ratings of underground cables and e-mobility. The increased use of renewable energies and new loads such as e-mobilities and heat pumps confronts the grid operators with new challenges. The required grid extension can be reduced if the grid structure is used in the best possible way. And for this purpose, a time series-based method is developed. Here we want to increase the transmission capacity of the cables, and the method also determines the time series for rest, loads, and e-mobility. And then we can investigate the effect of the dynamic current ratings and the increased use of the e-mobility. And this method is applied to two German real medium voltage distribution grids. For the calculation of the dynamic current rating, we developed a thermal model for the heat balance. In the slide, you see the cable in the ground, the backfill material around them, the mother soul, and the different layers of the cables, like the insulation, conductor, the shed, and the jacket. And the model, we have the current flow to feed this cable. We need a temperature distribution in the cable, and the sole terminal resistance between the power cable and the ground surface. And also the layout for the cable is important. The ground as well. And the most important factor is the terminal resistance of the sole, because this is changes the moisture content, and if the cable is too warm, then we get a dry zone around the cable, and this leads to a higher terminal resistance around the cable, and then the ground dry out, and so we can specify two different thermal conductivities, one for the dry zone and one for the wet zone. And in this figure you can see 4 different curves for the current ratings of the cables for different temperatures. The red line is for the nominal current rating, like 400 amperes. The blue line is for the current rating without drying zone. And the green line is with the dry zone, and the orange is the dry, if the zone drying out begins. And for my study, we use the current rating from the orange line down to -5 degrees, and then the green line from -5 to the end. And at 20 degrees, the current rating is under the nominal current rating. Then you can see here the simulation process. Before the simulation starts, the method selects a medium voltage grid. Then the simulation starts. Then we model the input data for the substations. For that we use a climate model for the renewable energy sources. We have the installed capacity of these sources and the time series to the high voltage grid. So we can now calculate the load time series. And if e-mobility, if you want that to analyze, then we must model this charging profiles. And for this we have a trip-J model. This model uses driving profiles, and with the battery capacity of the cars, and then we can model the charging profiles, and the charging profiles and how much EV vehicles at each substation we have. So we can now calculate a time series, the new one. Then if the dynamic current rating is calculated, and after that the time series based load flow calculation starts, and then we can analyze the results if we use the immobility or not, or the dynamic current ratings. And now we see here the results for one grid. It's a load-dominated grid. I have another grid with more renewable energy sources, but you can find it in the paper. On the left side, we have without immobility, and on the right with immobility. And the left box plots are with the nominal current rating, and the right box plots with the dynamic current rating. And you can see that for both, the transmission capacity increase. Here it decreased because the main value decreased, and the maximum value also decreased for the most of the lines. Only for some lines the maximum value increased. This is because in summer the permissible value for the current rating is lower than the nominal current rating. And with the immobility, the load increased a little bit, not very much. So the immobility don't cause overloadings. The transmission capacity can be increased. I say it. And the conclusion is that the dynamic current ratings lead to increase the distribution capacity without endangering the mechanical stability and the insolution resistance of the cable. And the grid infrastructure can be used more efficiently with reduced and limits the need of grid reinforcements. And we have extended grid integration potential for RES and immobility. And for future studies, the influence of the expansion of RES and new consumers on the voltage band and the line loading can be evaluated, and the consideration of suitable measures such as grid expansion, containment of RES, or renewable power consumption. And the method can also be applied to high voltage grids to consider the current ratings for overhead lines and underground cables. Thank you for your attention.